last lecture. Oh. Right, so I'm aware that at least in this course you've seen quite a breadth of material from hydrology to petroleum geology and hazards, and finally all deposits. So I'm wishful if I think that I made all geologists of you. Hopefully at least some. And all deposits involve a lot of complex processes and whatnot to form. But if you could come out of this course with at least some understanding of the most important processes that lead to ore formation, I'd be happy. That's a place in Western Australia with red dirt everywhere because of the iron gets oxidized. And this is a place in Japan with a volcano in the background that used to be mined for sulfur actually. And these fluids here, hydrothermal fluids percolating into the sea, into the harbor, and forming these oxidations. Anyway, so this was one of the first slides in the first lecture, and was basically what we wanted to get out of this module. And as I mentioned, understanding the processes that lead to ore formation, relating the particular deposits to particular settings and metals, and some familiarity with major ore minerals, with some of you getting, some of you not as much from the lab this time. It was painful to mark. Anyway, let's say that. But they're right. Let's just do the hardest things. Well, as long as you do well. So, metals association. We've got from rift environments, whether they are continental rifts or intraoceanic rifts, we can get different metals and deposits like SEDEX, continental rifting, and the HMS, for instance, near mid-ocean ridges, and these come associated with different metals. And in collisional settings, whether we have a subduction zone or not, we can have, again, different deposit types from porphyry, skarn, epithermal, to orogenic gold. So there is a link between tectonics and the ore processes that lead to ore formation and the particular metals that these processes or these deposits yield. But talking of processes, what processes are essential for the formation of all the deposits? Think in terms of cooking. What do you need when you want to make a soup?
Heat.
Heat? That's later. First you have to go and do some groceries. You just have a stove. It's not going to help. So what are the ingredients in an ore deposit? What's essential? The essential ingredient?
Minerals.
Minerals is later, but elements or metals. So we need a source of metal. And metals in the earth are basically contained either in the mantle or the crust. So we've got the metals in the mantle or the crust. What do we want to do next?
Heat them.
Mobilize.
Well, what does that lead to? Because the mantle and the crust, they are not ore deposits.
Oh, actually add water first and then heat them.
Water, maybe. Right. Well, we want to mobilize them. Okay? So starting from the mantle that contains, or the crust that contains metal, we want to kind of get the metals out of the mantle, the crust. by either partial melting or leaching. So now we've got a mantle with some partial melt that contains metals, or a crust with some leaching fluid that contains metal. What do we want to do next?
Accumulate them?
Before you accumulate them,
Rise up?
yeah, you want to transport them. Either through a magma from the mantle to go towards the surface, or if you are leaching the crust, you want solutions, hydrothermal solutions that can basically allow these metals to migrate. Migraine is what I got yesterday marking from the site of the original residence to where the deposit is going to be. So once we have the fluids or the magma that is carrying the metals, what's the next step? You mentioned it before. You mentioned it. Say it again. You said it before.
I said a lot of stuff.
But the next step is basically enriching and precipitation. So through a variety of processes, we can fractionate a magma, we can mix magmas, we can assimilate some kind of material into a magma to saturate particular phases, or we can boil hydrothermal solutions and make them react with whatever rock is available, and that causes basically precipitation of the metals. And then there is a last step, which is not essential, but is in some cases preferable, which is well, accumulation is kind of included in this step. I'm referring to further enrichment in case of supergene enrichment of primary ores, which in some cases can make them economically viable. So these are basically fundamental processes that you need in order to form an ore deposit. And independently of the ore deposit type, whether they are magmatic, hydrothermal, or sedimentary, those processes are somehow all needed to form a decent deposit. So looking first at magmatic ores, or magmatic ore deposits, and as I mentioned, the source of metals is either the mantle or the crust. And these are two plots of relative proportions of all the elements of the periodic table. In either, this is chondrite, which is basically meteorite, what formed the solar system originally. So it can be approximated to a bulk composition of the Earth, which is mostly mantle, so we can estimate more or less that the mantle contains element in these relative abundances. And the mantle is rich in elements that are usually compatible in magmas, such as nickel, chrome. As you can see, the sphere or the circle for nickel and chrome is bigger than it is in the crust. Incidentally, this is the same diagram, but for the continental crust. Whereas in the continental crust, we tend to have enrichment of those elements that are incompatible in melts. And of course, the crust forms over billions of years by partial melting of the mantle, intrusions or eruptions. And so we need those elements that are left over in the melts at the end to form continental crust. And these are usually elements such as tungsten, barium, lead, the rare earth elements. As you can see, there is much larger abundance of these elements in the continental crust compared to the mantle. So once we have the mantle or the crust, in order to mobilize them, we need to basically partially melt the crust or the mantle for magmatic ore deposits, magmatic ore. And this is again the diagram of concentration in a liquid versus the concentration in the original material. The mantle, for instance, depending on the degree of melting and the distribution coefficient of a particular element to the bulk. So if you can see again, for very low distribution coefficient, we've got a sudden enrichment as soon as you start melting, and then a dilution of that signature. And for elements that instead like to reside in the mantle, we need to melt more and more of the mantle for the crust in order to enrich them. And this is represented here with, for instance, the platinum group element metals that are enriched due to the melting of sulfides in the mantle, and after that they are just diluted as you increase the degree of melting. Whereas if we are interested in nickel, we need to melt more and more of the mantle in order to enrich nickel in the resulting magma. Transport in magmatic ore deposit is by magma, really. And depending on the composition of these magmas, we all have different metal associations related to the resulting deposits. Now, the precipitation from magmas, we can start with simple fractional crystallization. Again, you should be familiar with this diagram. You've seen it in the second lecture. We start with a melt with a composition around here, and we fractionate olivine. We move it away from olivine until we hit the autectic, and we start to crystallize both olivine and chromite, for instance. And that stage, basically we remove olivine and chromite from the melt, and we form these disseminated ore mineral within a cumulate of silicate minerals. But as we saw, that doesn't explain certain characteristics of certain ore deposits. For instance, the massive sulfides and oxide layers, massive, supposed to disseminate. And in order to form these massive layers, we need a different process, and this can be, for instance, mixing of relatively evolved and a relatively primitive melt, which saturates the ore phase and causes it to crystallize at once and settle and form these massive layers. And depending on when mixing might occur within a magma reservoir or magma chamber, we might end up with a new melt, basically percolating towards the bottom of a magma reservoir, or later the new melt might actually be less dense than the residual melt in the reservoir, so we've got this new melt really floating on top, more efficient mixing, and better precipitation of these massive oxides and sulfide layers. Another process which applies to, for instance, nickel deposits in chromatites is by assimilation of sulfur from the country rock or from the basement. So we've got basically sulfur being put into the system from the outside, and so increasing or reducing the solubility of sulfides, and hence precipitating the sulfide particles. Another process is by assimilating felsic country rock, and on this diagram this is basically represented by a magma mixing with quartz, representative of felsic country rock, and saturating phase with sulfide or oxide phase, hence forming either disseminated or massive ores. The last way of precipitating ore minerals from a magma is by extreme fractionation. So again, in this diagram, where we have the degree of crystallization from non-crystallization to all crystallized, an element that is incompatible in the crystallizing phases, or in the case of, for instance, tin, that tin doesn't go into feldspars and quartz and olivines and pyroxenes, so it just remains enriched in the residual melt up to the point at the end where we've got basically very little melt left, and the metal is saturated with respect to the melt, and we'll have the dissemination as we saw in the lab. Alternatively, we can have then fluid migrating away from these last magmatic residues and forming pegmatites. So just to recap, for magmatic ore deposits, we can have layered intrusions that are targets for chrome and PGEs. We can have nickel chromatites and late magmatic stages or pegmatites that are related to these type of elements and form deposits like that. And you knew this yesterday. With disseminated ores again, where the sulfide in this case just occurs scattered throughout a matrix of silicate minerals, or massive ores where we got these horizons of basically just oxides or sulfides. On to the second type of ore deposits, hydrothermal ore deposits. And the source of metals, well, again, metals reside in either the mantle or the crust on Earth. But particularly near subduction zones, we've got these input of possible fluids and metals from the subducting and dehydrating plate, fluids percolating and migrating through the mantle, goes partial melting, and again we've got metals entering the melt phase. And for a while the metals will be transported within magma, but we are moving on from that. Another possible way, or another host for metals related to hydrothermal ores, is just the crust, where we have fluids percolating into the crust and leaching the ores away in order to form ore deposits. In order to mobilize then the metals, as I said, we've got either fluids percolating and into melts, or percolating through the crust in order to leach the metals from the crust. And we've got a variety of fluid types from magmatic. So in order to mobilize a fluid containing metals from a magma, we need to boil the fluids basically. And this is done either through first or second so-called boiling. Can anyone tell me what's the difference between first and second boiling? What's first boiling? What is it due to?
Decompression.
Pressure?
Decompression.
Good. Decompression. Very good. And the second boiling? Second boiling is basically as you increase the concentration of the fluid water in the melt, for instance by removing crystals through fractionation, that at some stage will saturate the water and cause it to separate from the magma. So it will have a separation of this magma and water. And of course, in order to allow many of these metals to be soluble in these fluids, whether they are the magmatic or whether they are meteoric or crustal fluids, we need complexes which bind with metals and allow them to be more soluble than they would otherwise be. So once we've got fluids, we need to transport them to the site of mineralization, and that usually occurs either through porous flow, through whatever medium, porous rock, or flow along fractures and faults. As is the case here, for instance, we've got the intrusion, water separation, and flow through cracks and fractures and bridge pipes above the intrusion. If we don't have magmatic input, we just have fluid flow through the crust in a case of gravity or compression-driven flow, also associated with dehydration due to metamorphism. So we've got this large-scale crustal fluids flow. In a case where we are close to a heat source, we've got this thermally driven flow, where we've got seawater or water percolating into the ground and being heated up, and so becoming thermally buoyant and returning to the surface. Or else we've got this structural control which allows fluids to flow through faults and fractures. And the precipitation is basically summarized by this picture. Basically, lowering temperature causes a decrease in the solubility of the complexes, which causes them to dissociate, and basically we've got precipitation of metals. Or else we can react whatever fluid with carbonate, which usually causes the neutralization of the acidic fluid that causes the precipitation of metals. You can do it by boiling. This boiling is not the same thing as the first and second boiling that separates fluid or water from magma. This is basically the boiling of the fluid itself that then releases the vapor, and the vapor will contain certain components that were necessary to form the complexes and hence allow the solubility of the metal. If we remove those through boiling, we basically precipitate the metals and the whole minerals. Or else the last is by mixing hotter acidic water with cooler, more neutral waters. Again, we have the process of ore precipitation through the breaking of chemical complexes. And so we can form a variety of deposits. There's kind of a spectrum from porphyry to epithermal to skarns. As we are closer to the intrusion, we can form, even closer to the intrusion, we might form those so-called Greisen deposits. Or further into the country rock, into veins, we might form porphyry copper deposits, or porphyry molybdenum deposits. As the fluids then migrate further towards the surface, we can form high sulfidation, epithermal gold deposits, or if we neutralize the fluids, low sulfidation deposits. And if we have a carbonate rock somewhere in the vicinity, we might basically neutralize the acidic magmatic fluids directly onto the carbonate and form these skarn deposits. Onto another spectrum of deposit types, BHMS, ZX, and MBT. What does the BHMS stand for?
Volcanic hosted magma.
Magnetite.
Massive silver.
ZX.
Sedimentary excited.
And MBT.
This is a big belly type.
Very good. Right, so in this type of deposits, we basically have lesser magmatic input, so it's more fluid leaching metals from the crust and reprecipitating them on the surface, as in the case of mid-ocean ridges, for instance, or volcanic settings, or close to volcanic settings, where we have basically the fluids leaching the basement, circulating, and then precipitating the metals based on the temperature. And we go from a very hot pyrite zone in the center to the outside lower temperature where we have zinc and lead precipitation. On to ZX, where we don't have the kind of volcanic proximity, but the process is similar because we've got fluids, crustal fluids again, reaching the surface or percolating through soft sediments, and the temperature difference again causes the precipitation of coppers and zinc and lead sulfides. And in MVT deposits, basically larger scale crustal fluid flow and reaction with carbonates, but overall similar processes. And the last hydrothermal deposit type is orogenic gold, where we've got metamorphic devolatilization or some potential magmatic input of fluids on large crustal scale faults, so fluid over protracted length of time and large volumes. And we've got the gold, which is transported as a bisulfide complex, and then the precipitation, which can occur either by phase separation through boiling or by reaction with the country rock, which again consumes H2S, causes the dissociation of the gold bisulfide complex and precipitates the gold. And the two processes will be related to either free gold or gold associated to sulfides. And this same diagram we saw a couple of lectures ago, a bit simplified. I'd be very happy if you would be able to kind of explain at least these different deposit types related to hydrothermal systems. And we've just seen them now with BHMS and ZX, Mississippi volatile deposits, the continuum between skarn, porphyry, craisins, and epithermal deposits, and the orogenic gold deposits, and how they relate to either meteoric or seawater or magmatic and metamorphic fluids. And then, as we mentioned, the fifth step, which would be ideal, the supergene enrichment of certain deposit types. So we've got basically from the surface, meteoric water, rain and whatnot, percolating and leaching copper, zinc, lead from the sulfides. These fluids then percolate down and form oxidized or carbonate versions of these metal ores, leaving behind just iron oxides and iron hydroxides. We get then the formation of malachite, which is not an oxide, smithsonite, which is a zinc carbonate, cerussite, which is a lead carbonate. And then further percolation down would then react the same fluids and substitute the iron in the original pyrite, chalcopyrite copper, and hence forming these enriched copper sulfide minerals. Last, close to the surface, superficial ore deposit types. Again, the metal source. It's got to be the crust in this case because the mantle is quite deep. There is no way that superficial processes can reach the mantle unless we have a ophiolite belt, which is part of the mantle on the crust or on the surface. But anyway, again, we've got the superficial portion of the crust, which can be chemically weathered or contains metals, or the crust which is physically eroded and the metals contained are removed. The mobilization in surficial ore deposits, which is not necessarily a mobilization of the metal we are interested in, but might just be the mobilization of everything else we are not interested in. And that can occur by dissolution, mostly by water, and certain elements are more soluble in water than other elements. Or through hydrolysis, which is, again, we saw that on Monday, the breaking of the bonds in water to break down certain minerals and forming other minerals, and in the process basically leaching potassium and later on silica. Mobilization in a physical sense is just basically erosion with waters and stream carrying away bits of land. And the transport, basically, as I mentioned, the transport might not necessarily be the metal we are interested in, but those that would just pollute the deposit. And that's the case, for instance, of laterites, where we want to leach everything we are not interested in. We might, however, be interested in leaching and transporting those metals we are interested in to form supergene enrichment of primary hypogene ores, or in physical terms, basically just transportation by water of certain metals such as gold or ore particles, rutile, ilmenite, and the like. Again, there's a bit of overlap here, but the precipitation, that's in inverted commas, because it's not necessarily the precipitation of the metals we are interested in that counts, but it's the removal of what we are not interested in. As I mentioned, we are interested in just the residual aluminium and nickel in laterite, for instance. As you should remember, we've seen this on Monday, the percolation and weathering front, basically removing and oxidizing first sulfides, removing a bunch of elements, and later just leaving kaolinite and clays. Later, hopefully, the silicon gets removed as well, so we just enrich the clay on the aluminum, and we are left with both sides. We can have the precipitation and replacement of hypogene ores, as I mentioned before. This circulation of the metals we are interested in into the lower oxidized and reduced zones, where they can displace, for instance, metals such as iron we are not necessarily interested in, but replace them with copper and form enriched sulfides. And then lastly, we've got the settling from streams to form placer deposits. In the case of banded iron formations, the precipitation here requires an input of iron, reduced iron, Fe2+, into deep sea anoxic waters, and then a process that basically causes the iron to oxidize, mixing with oxidized water, near surface waters, and the precipitation of these iron hydroxides. And lastly, especially for banded iron formation deposits, supergene enrichment might also come in handy. We have basically shallow processes that strip electrons from greater depth and cause again the oxidation of iron to iron 3+, and so enrich the ores, and in the process releasing a bunch of hydrogen which can just dissolve silicates and carbonates that were there just to pollute the ore. So, just to give you some warning, these exam, my section of the exam, so the all deposits, part of it will be 8 questions, which will be more or less worth same amount of points, so I should try to spend about 50 minutes on each. And be clear and concise. So I hope not to see brain dumps, because it's to your detriment. If I have to hunt through a bunch of text for key interesting terms, I might not find them, and so not give you marks you might deserve. And use diagrams and bullet points. So we've seen many diagrams throughout the lectures. You might want to maybe think of the most important and be lenient. Be merciful on me.